In the last lecture, we had examined mass diffusion first in gases and then in liquids. I had told you that the mass diffusion is because of transport of molecules across a surface in a gas, the physical transport of molecules. And the transport of molecules across a surface occurs from distance approximately 1 mean free path above and below the surface. At these two locations, the concentrations are different, and because of this there will be a net flux that is proportional to the concentration variation across a distance of the order of the mean free path. That concentration variation across a distance of the order of the mean free path is equal to lambda times dCA by dZ. Okay. Concentration difference times the velocity is the flux, velocity perpendicular to the surface. Okay. So, the concentration variation across a distance of the order of the mean free path across the surface is b lambda times dCA by dZ times the velocity across the surface. The velocity across the surface is of the order of the root mean square velocity times a constant, okay, which was Aj times Vrms. Okay. So, that is the velocity with a negative sign, because concentration is downward. If the flux is downward, if dCA by dZ is positive and concentration above is greater than the concentration below. Therefore, we got a diffusivity as some factor, okay, some constant, dimensionless constant times Vrms times the mean free path, okay, in a gas. And we had estimated that under conditions of standard temperature and pressure, Vrms is square root of 3 kT by m, which is roughly between 500 and 2000 meters per second for oxygen, nitrogen to hydrogen. Okay. We had further estimated the mean free path from the time taken between successive collisions, and that is of the order of 1 over the molecular diameter square times the number density. Okay. And this was approximately 0.1 to 0.05 microns was the estimate. Okay. 0.1 to 0.05 microns was the estimate. Okay. And based upon this, we got the diffusion coefficient as 10 power minus 5 meter square per second, okay, in gases such as nitrogen, oxygen, okay, at room temperature and pressure. Okay. This we had calculated for water vapor in air, approximately 10 power minus 5 meter square per second. We had discussed diffusion in liquids. Difference in gases, molecules travel many times their diameter between successive collisions. In liquids, the distance between molecules is comparable to the molecular diameter. So, a molecule is executing some random motion within a cage formed by surrounding molecules, and the physical transport of a molecule in any direction requires cooperative motion, so that other molecules move in such a way that space is created for this particular molecule to move in a direction. Because of that, the estimate of the molecular diameter of the diffusion coefficient based upon the molecular diameter and the RMS velocity is an overestimate. The diffusion is slower because molecules have to physically move for mass diffusion to take place, and the estimates are in the range 10 power minus 9 to 10 power minus 13 meter square per second, okay, for molecules in air. The estimate for the mass diffusion coefficient came from Brownian motion. We had calculated the Brownian diffusivity using dimensional analysis in a liquid in the low Reynolds number regime, where inertial forces are not important, because these processes occur at very small scales of the order of a micron or so. And we had used the Stokes-Einstein relation in order to estimate the diffusion coefficient. This is strictly valid only when the diameter of the diffusing molecule is much larger than the diameter of the diffusing particle is much larger than the molecular diameter. In that case, this is an exact relation. When the sizes become comparable, this cannot be used quantitatively, but can be used only to make an estimate. And the other equivalence that we made here was between Brownian diffusion and diffusion due to a concentration gradient. Based upon that, we had calculated the diffusion coefficient, for example, for nitrogen molecules in air, and we had got an estimate of about 10 power minus 9 meter square per second, which is the correct order of magnitude, and even quantitatively it is close to the actual measured value. Okay. So, this can be used for estimating diffusion coefficients. Okay. So, next we will proceed to discuss thermal diffusion. Okay. Next we will proceed to discuss thermal diffusion. Okay. First in gases and then in liquids. In gases, the picture is exactly the same as that for mass diffusion. The transport of molecules across a surface, okay, is what results in thermal diffusion. When there is no variation in temperature, you have equal numbers of molecules going above and below, and all of these molecules have the same energy, and therefore, there is no net transport of heat, okay, or thermal energy. Okay. However, if I have an energy gradient, okay, if I plot temperature versus Z, and that temperature varies with Z about this location of the surface Z naught. So, I have a variation in the temperature. The molecules that are coming downward are coming from a distance comparable to the mean free path above the surface, where the temperature is higher. Therefore, their thermal energy is higher. Molecules that are going upwards are going from a distance approximately 1 mean free path below the surface, where their temperature is lower, and therefore, the molecular energy is lower. Therefore, in this case there will be a net transport of energy from above to below when there is a positive temperature gradient, or the temperature increases with Z. How do we estimate what is this temperature, this thermal flux due to this temperature gradient? Okay. The molecules that are coming below are coming at a distance approximately 1 mean free path above the surface. Okay. So, this the flux is going to be equal to some coefficient times Vrms. So, the flux is the average normal velocity times the concentration. The normal velocity is a factor times the RMS velocity. Okay. So, this is the flux, the velocity perpendicular to the surface is AE times Vrms, where AE is some constant, times the thermal energy at a location Z naught plus B lambda. Okay. In this case, I should note that Vrms also depends upon temperature. Okay. So, I should put in a temperature dependence on distance here as well. The molecules that are going upward are going from a distance approximately 1 mean free path below the surface. Okay. So, therefore, Qz going upwards is going to be equal to AE Vrms at Z naught minus B, I am sorry, B lambda here. Kindly note this is not Vrms, this is B lambda times H at Z naught plus B lambda. Okay. There is a mistake here as well. Okay. So, this will be Z naught plus B lambda. Molecules coming downwards come from this location, and this is Z naught minus B lambda. Molecules going upward come from this location. Okay. So, the total flux Qz is equal to AE into Vrms at z naught minus b lambda, or total flux. Flux is positive if it is in the plus z direction. Okay. Flux is positive if it is in the plus z direction. So, this is going to be equal to q z upward minus q z downward. Okay. Flux is going to be the flux upward minus the flux downward. Okay. Where H, the symbol H I have used is the thermal energy density, okay. The enthalpy density actually if you are at constant pressure process, okay. The enthalpy density if you are at a constant pressure process. Okay. So, just as the mass flux was equal to the RMS velocity times the mass density or the concentration at that location, the energy flux is equal to the root mean square velocity times the energy density, okay, or the enthalpy density at that location. So, therefore, q z at z is equal to z naught, okay, is equal to A e into Vrms h and this product, okay, can be expressed as the product at z naught, okay, okay, plus, okay, in this case because I have minus sign here, this is minus b lambda d of Vrms h by dz at z is equal to z naught. Similarly, the product above the surface Vrms at z naught plus b lambda h at z naught plus b lambda is equal to Vrms at z naught h at the location z naught plus b lambda at z is equal to z naught. So, substituting these I will get, okay, the q z is equal to A e into okay, minus the value at z naught plus b lambda, which is Vrms similar calculation to the mass concentration, except that we have put the enthalpy density instead of the mass density, and the root mean square velocity is also a function of position because it is a function of temperature. Okay. And once again these two cancel out, okay, and this mass flux turns out to be equal to minus 2 A E B lambda V R M S sorry at Z is equal to Z naught. Okay. So, now in a gas the enthalpy density H is equal to rho C p times T, okay, where T is the absolute temperature. Okay. In a gas the enthalpy density is equal to rho C p times T, where T is the absolute temperature. Okay. And we know that VRMS is equal to root of 3 kB T by M. Okay. Which implies that VRMS times H is equal to rho CPT root of, kindly note this should be the molecular mass. Okay. Okay. And the derivative of that, okay, d by dz of VRMS H is equal to, okay, this is proportional to T power 3 halves. Okay. So, the derivative will be T power half times dt by dz. Okay. So, this will be equal to rho Cp root of 3 kB T by M. Okay. So, 3 halves here into dt by dz. Okay. Let me take the derivative a little slowly here. Okay. So, this is equal to d of VRMS H by dz. If the density, viscosity, Boltzmann constant, etc., are all constants, then this is equal to rho Cp into root of 3 kB by M d T power 3 by 2 by dz. Okay. Is equal to 3 by 2 rho Cp into root of 3 kB by M T power half dt by dz, okay, which is what I have over here. Okay. So, I can simplify this as 3 by 2 rho Cp VRMS, okay, dt by dz. Because square root of 3 kT by M is just VRMS. So, this gives me the expression for Qz here. Minus 3 AE B lambda rho Cp VRMS dt by dz. This has the exact same form as Fick's law, except that you have, so this whole term is the thermal conductivity. Okay. Compare this with Fick's law, Qz at z is equal to 0 is equal to minus k dt by dz at that location. Okay. So, this has the same form as Fick's law, okay, in which the thermal conductivity is K is equal to 3 AE B rho Cp lambda VRMS. Okay. So, this is the same as Fick's law of diffusion with this particular thermal conductivity. Okay. So, this gives you a microscopic expression for the thermal conductivity based upon the density, specific heat, lambda and Vrms. Okay. Thermal diffusion coefficient is equal to K by rho Cp. Okay. It's equal to 3 AeB lambda Vrms. So, the thermal diffusion coefficient is also proportional to a constant times the mean free path times the molecular fluctuating velocity. Okay. This was the same as the mass diffusion coefficient, okay, up to within a multiplicative constant. Okay. So, in a gas, both the mass and the thermal diffusion coefficients have the same form. They are equal to the RMS velocity times the mean free path. Okay. Turns out we will see next that the momentum diffusion coefficient also has the exact same form. The thermal conductivity is equal to this thermal coefficient diffusion coefficient times rho Cp. Because we have expressed the conductivity in terms of temperature, the diffusion coefficient is in terms of the density of the of energy. Okay. If you recall, when we wrote the diffusion equation, the flux is equal to a diffusion coefficient times the density of that quantity per unit volume, the change in density per unit length. Okay. So, if we express it in terms of dH by dt, okay, so Qz can also be written in terms of the enthalpy density as minus 3 AE B lambda Vrms dH by dt. Okay. Expressed in this form, the diffusion coefficient is equal to the mean free path times Vrms. Okay. So, in gases, because the mechanism of diffusion is the same, mechanism of thermal diffusion and mass diffusion is the same, both are due to physical motion of molecules across a surface. Therefore, the expression for the diffusion coefficients are also the same. Okay. They are both proportional to, they are both equal to a constant times the mean free path times the root mean square velocity. The thermal conductivity is equal to rho Cp times this. Okay. So, that is how you get an expression for the thermal conductivity. Okay. If you recall, I had given you a more exact expression for the thermal conductivity for the mass diffusion coefficient in gases. For the thermal conductivity, you can get a similar expression. For a hard sphere gas, this is equal to 25 by 32 molecular diameter square 1 by gamma minus 1 Kb cubed T by pi m whole power half. Okay. Where gamma is equal to ratio of specific heats. Okay. It's equal to Cp by Cv. Okay. So, this is the more exact expression for the thermal conductivity in a gas. The thermal diffusion coefficient is this times rho times Cp. Okay. Note that the mean free path, okay, 1 by root 2 pi n d square, okay, and Vrms square root of 3 Kb T by m. Okay. So, if I multiply this by rho and Cp, okay, I will get the thermal conductivity which has this particular formula, okay, for a hard sphere, ideal hard sphere gas. Okay. And this expression can be used to estimate the thermal conductivity in gases. Okay. I will give you an example. Okay. The thermal conductivity of air consisting of diatomic molecules with molecular weight 29 grams per mole. Oxygen is 32, nitrogen is 28. As an average, I have taken 29 based upon the compositions. And molecular diameter 3.7 angstroms. Diatomic molecules, okay. Cp is equal to Cv is equal to 5 by 2 kb, okay. 5 degrees of freedom, 3 translational, 2 rotational. 5 by 2 kb is Cv. Cp is equal to Cv plus k, so 7 by 2, and gamma is equal to 7 by 5. Okay. Ratio of specific heats. Okay. Therefore, K is equal to 25 by 32 dm square into 1 by 7 by 5 minus gamma minus 1, okay, into kb cubed T by pi m whole power half. Okay. Molecular mass is 0.029 kg by 6.023 into 10 power 23. Okay, that is the molecular mass, and you have to take the square root of this entire thing. Okay. And you can do this calculation, and finally you will get 0.032 watts per meter per Kelvin. Okay. So, this is the thermal conductivity of air, okay. And you can easily see that you will get in the end watts per meter per Kelvin, because you have a diameter square in the denominator and kg in the denominator, and this Kelvin you have per Kelvin the whole cubed here, and you multiply by one factor of Kelvin, you will get a per Kelvin coming out. Okay. So, you can verify that this is dimensionally accurate. Experimental, at this temperature, this is 0.026 to 0.028 watts per meter per Kelvin. So, with this simple model, we were able to accurately predict what is the thermal diffusivity, okay, of a gas in air. Okay. And because gases, the mass and thermal diffusion coefficients, the transport of mass, momentum and energy are by the same mechanism, that means that the Prandtl number, okay, is equal to nu by alpha. We will see next momentum diffusion coefficient also is proportional to Vrms times the mean free path. Therefore, this is equal to order 1. Okay. So, typically if you know what is the viscosity, you can estimate what is the thermal diffusion coefficient. Okay. For polyatomic molecules, there is a formula that actually gives you this. Okay. Which is that the Prandtl number is equal to Cp divided by Cp plus 1.25 kb by m, where m is the molecular mass and Cp is the specific heat with dimensions of energy per unit mass per unit degree centigrade. Okay. So, this can be used to find out what is the diffusion coefficient, the thermal diffusion coefficient if you know what is the momentum diffusion coefficient. So, in all of these cases mass, momentum and energy, gases, mechanism is the same, diffusivities are all proportional to the mean free path times the molecular diameter. Okay. And you can, and therefore, the diffusivities are all of equal magnitude for mass, momentum and energy. So, in the next class I will continue this. I will briefly discuss diffusion of heat in liquids and then go on to momentum diffusion. Okay. So, I will continue this discussion of diffusion in the next lecture. I will see you then.